So I'm not gonna ask who's read the black book on continuous integration. If you haven't, you should read it. Um, so Dave is the author of that book. He's also a consultant. He's the main event tonight. I'm not going to do much more of an introduction, although I will say that we had a mention of the space shuttle. Dave has promised that there's going to be some mention of Saturn V, which is one of my favourite things ever. So thanks, Dave.
Thank you. Thank you very much. Good evening. I'm not going to go there because there's a temptation to debate some of that stuff. Really interesting talk, but maybe when we have beer afterwards. I want to talk about a slightly different take. One of the things that I'd like to pick up on is in there was a description of agile without discipline, and I agree. I think that's a terrible thing. So my talk really is about what does agile with discipline look like. That's one way of thinking about it. What I really want to talk about is I want to talk about software engineering. I want to talk about engineering. I spent a lot of my career, the early days of my career, with job titles like software engineer. I was a junior software engineer, and then I was a software engineer, and then I was a senior software engineer and stuff like that. And during that time, I didn't do any engineering whatsoever. I used to write code, but it wasn't engineering. And then a bit later on, I started working in places where we started disliking the term engineering. We talked about it being an analogy, and it was a bad analogy, and it was the wrong kind of thinking, and we weren't really, it was the wrong mindset to think of ourselves as engineers. And we didn't have job titles like that. We called ourselves software developers or craftspeople or all sorts of different things, but we weren't engineers. And then later on, I did some quite hard things. I did some interestingly difficult, I was involved in the solution to some interestingly difficult software problems. And we came up with a way of working that I think started me thinking about engineering again. And that's really what I want to talk about. So I think that when we think in terms of software engineering, we'll often start off and we'll think about things like this. This is to software engineering what a soldering iron is to electrical engineering. It's not software engineering. This is a tool, and it may or may not be a useful tool, but it's only a tool. This is not what I'm talking about. We might think about this. We might think about the processes that we use to address the problems in software development. We might come up with things like this. This is Scrum. Anybody, any idea how many times the Scrum documentation mentions the words code or software? Anybody? Zero. So it's a good project management discipline. It's not the only agile project management discipline, but it's a decent one. But it says nothing about software engineering. It says nothing about software development. It says applicable to plumbing as it is to software development. And it's a good way of doing your plumbing. So this isn't software engineering either. In recent years, the idea of software craftsmanship has come up, and craftspersonship is a bit of a mouthful, but that's what we should be saying. We should be saying something else that's gender neutral. I don't mean to be disrespectful to female craftspeople in the audience, but there's the move of software craftsmanship and the idea of it being a creative discipline and that being a better metaphor. And I think there's something to say for this, but this too is not engineering. The trouble with craft is that craft is very variable in terms of the output of what we're trying to deliver, and engineering adds something else to craft, which I'm going to go into in a bit more detail. I think if we think kind of on the long, the long scale of of time, of history, there are really three principal divisions of the way in which human beings have made things. There's been kind of craft-based production, and that was the way that human beings made everything for thousands, if not tens of thousands, maybe even hundreds of thousands of years. And then later on, sort of the middle of the 19th century, we started coming up with approaches to mass production. The first mass production was in the American Civil War, building rifles for the northern states, and it was one of the reasons why that war was particularly horrific, because they were able to make lots and lots of rifles. It was the first really mechanistic war. And there's an interesting story about a man going to the man who wanted to get the contract for the rifles, selling them to the northern states, going to Congress with a bag full of components, and he tipped them out on the floor of Congress and got the congressman to select different components from which he built a rifle. And that wasn't possible before. That had never been possible before because there wasn't standardization of components. For building physical things in a predictable, repeatable pattern, mass production is quite an effective strategy. It allows you to do these things. It allows you to do things that you couldn't do before. Except that's not our problem. We don't have the problem of production. Production for us is pressing a button and the compiler whirs, and that's it. Our problem is design. It's a different kind of problem. Later on, there was kind of a refinement to some of those ideas. And at the end of the Second World War, Deming went to Japan and started coming up with ideas that led to the evolution of Toyota had some of those ideas beforehand, but the combination kind of led to the generation of lean production techniques, lean manufacturing techniques, and that informed the production. Most modern, efficient production systems are built on lean production techniques. So where, if we were going to use these as models for where we are as a software industry, where are we? So I think we're not doing mass production, and I think we never will, because I think it's the wrong model. Mass production is a way of optimizing for production processes. Mass production works really well when you have a predictable, understandable steps that are repeatable, and software development isn't like that. Software development is varied. It's an exercise in discovery. I think we are currently a craft industry, and I think there are good reasons for that, because that's a better fit. It's a better fit for what it is that we undertake as software developers. This creative act of trying to understand and evolve solutions to solve problems in software, and the downside with craft is it's so variable, it's so unpredictable, it's so, on the whole, low quality. Just for a moment, imagine a craft-built version of that. It doesn't make an awful lot of sense. Even the prototype of a device like this requires massively complicated industrial capability. You can't build one of these in your shed. It doesn't work like that. If we are very wealthy, we might like hand-stitched leather in our cars, but on the whole, craftsperson-built things are lower quality. Engineered things are higher quality. That's the tolerances that we can work to these days, the materials that we can use, the processes that we can employ to build these things are more effective. So I think that where we should be aiming is really lean production. Those sorts of techniques, thinking more effectively about the efficiency and the effectiveness of the way in which we work. When we start working in some of these ways, the data that tells us the impact that has on our ability to create higher quality software more quickly, that satisfies users more fully, is quite dramatic. We see dramatic improvements in the efficiency of what we can create and its quality. I worked on a very extreme agile project, and we were in production for 13 months and 5 days before the first bug was identified by a user. These things are possible. These things are different. This represents a step change in capability for the development of software. So I want to explore that idea in a little bit more detail. If my clicker will work, I will. Hello? Aha. I appear to have a technical problem of some kind. Just one moment. Damn. Sorry, I'm going to reboot my computer. This happened to me earlier today when I ran through, and then it worked, and then it did, and now it hasn't. So what I'm talking about engineering as an approach. Come on, it's restarting. So the crafts-based approach allows us to create things, to explore, to innovate in that kind of way. But it gives us so much variable quality. The difference between a great performer and a poor performer is vast. The predictability, even within a team, is going to be variable. Sorry, I can now log in. So I think we should be looking for more lean production techniques. We've gone through this kind of evolution over time. Most manufacturing these days is using these sorts of techniques because it works better. It's developed empirically through discovery and experiment that those are better ways of working. Now, when I start talking about engineering in the context of software, weirdly, I tend to get involved in quite a lot of conversations about bridges. Nearly everybody says, yeah, but software's not bridge building, is it? And no, it's not. But then when we think about bridge building, often it's not what we're thinking of either. If you're building the first bridge for the first time ever in new materials across a span that's not been explored before, it's going to be a very, very different kind of process to building the same old suspension bridge that has been built 500 times across the world. This is an exercise in discovery. So bridge building is not necessarily what we think of it. So all engineering is not the same. House building is different to bridge building. Aerospace engineering is different. Chemical engineering is different. Electrical engineering is different. They're all different from one another. So one thing that we can be certain of is that software engineering, anything that we could consider to be an engineering discipline of our own, is going to be ours, and it's going to be in some ways unique to us. The other way in which engineering is different is in scale. When you think about physical devices or physical structures like these, it's fairly obvious that the engineering that went into these structures is different. When you think about software, not so much. If I think about the software that runs, I don't know, the search for Google compared to the software that runs my mum's cake shop, they're going to be, the engineering behind those are going to be very, very different, and probably should be. The engineering for a pacemaker or a space shuttle aviation control system or something like that are going to be different. And so engineering operates at different levels of scale as well. These are both engineered structures. The one on the left, the shed, if that was an IKEA shed, you can bet there was some kinds of engineering that went into that to make sure that the materials were just at the right price, and that the pitch of the roof was just correct to use the stress and all that kind of stuff. But it's going to be different to building the world's tallest building. They will have been doing finite element analysis, building models and putting them in wind tunnels and all kinds of things to do the engineering for those kinds of structures. So our engineering is going to be unique to us, and it's also going to vary depending on the scale and the nature of the software development that we're undertaking. It's probably time to start thinking about some definitions. And this is the definition on Wikipedia. And there's a bunch of definitions on other sites. They kind of have a bunch of words in common. So we talk about mathematical approaches, empirical evidence, scientific knowledge, using these to invent, design, and research things on an economic basis. And those are okay, but my kind of working definition for the purposes of this conversation this evening is this. This is what I have in mind when I'm thinking of engineering. Engineering is the application of an empirical scientific approach to finding efficient solutions to practical problems. I think that all of those words kind of add to the definition. It's all of them are important. So that's really what's behind my thinking for the rest of this. And for any kind of engineering discipline that I can consider worthy of the name in the context of software development, for me, it's going to embody these five ideas, these five practices. It's going to be iterative. It's going to employ feedback and treat that seriously. It's going to be incremental, allowing us to build things piece by piece. It's going to be experimental, where we can evaluate ideas and discard the bad ones and build on the good ones. And it's going to be empirical. We're going to measure our things in real life use and understand their impact. So let's deconstruct those a little bit more. So iterative. Iteration is the act of repeating a process to generate an unbounded sequence, not very interesting, or with the aim of approaching a desired goal, target, or result. We're trying to steer towards a particular goal, and that's what we're trying to achieve. Being iterative is important. It means that we can learn, react, and adapt to what it is that we observe. Quite like the adapt one at the end. It allows us to steer towards a goal. It allows us to navigate. This is one of the advantages of a more agile approach to solving problems, because it allows us to react to things that come up unexpectedly and steer in different directions. It's fundamental to any process of continual improvement. If we're looking to continually get better and better and better at what we do, an iterative approach is fundamental. It gives us more opportunities to learn. And that also gives us more opportunities to practice the skills, the techniques, the processes, exercise our understanding and improve that too over time. Feedback. Feedback is information about actions returned to the source of the actions. I think of continuous delivery in particular as absolutely fundamentally grounded in the idea of feedback. That was the idea that kind of got me interested in being involved in writing the book in the first place. Feedback means that we can observe the impact of our choices. It means that we can understand what the implications of those choices are. And it allows us to again, refine our understanding and build on it over time. As I said, I see this as fundamental to my favourite development approach, continuous delivery, and it's based on this model of feedback, as a pervasive tool in our approach to software development. It should be incremental. Evolutionary design, continuous design, evolutive design, or incremental design is directly related to any modular design or application in which components can be freely substituted if someone improved or can ensure better performance. I promised you something from the Apollo program. So here's my first go. So the Apollo program was interestingly a very modular system. So here are two modules that I would call out. That's the first module, and the job of that module was to get the whole spacecraft from Earth to Earth orbit. That's quite a hard problem, as you can see by the amount of spacecraft that's devoted to it. The top bit, which was here, and the lunar module, is also modular. So this is the command module, and then the job of this part of the spacecraft was to get from Earth orbit back to Earth. And is this part of the spacecraft, this is the service module, and its job was to get from the Earth to the Moon, and from the Moon back to the Earth again. This was really important, this modularity, because it's energy efficient. The original concept at the start of the Apollo program was essentially like a Wallace and Gromit rocket, where you had the whole thing that took off in one go, flew up to the Moon and landed. This was kind of the 1950s version of a moon mission. It flew, it landed on the Moon, and then it took off and it flew all the way back. That's very energy inefficient because you're moving lots and lots of stuff around. It also meant that it was composable. It meant that when you came to the disaster that happened with Apollo 13 and part of the service module exploded, you could reconfigure the system and compose it in different ways that the designers hadn't originally envisaged, and use it in different ways. This gives you flexibility and power. This is the other part of the modular system. This is the lunar module. And this too is in two parts. So you've got the lunar ascent module. Its job was to get the astronauts, the two guys that were on the Moon, from the Moon to lunar orbit. And the bottom part is the descent module. Its job was to land them on the Moon in the first place from lunar orbit. I've stolen this picture because I've talked about iterative and incremental, and they're kind of similar words, similar ideas. It's easy to get them confused. And this is the best pictorial version that I've seen of trying to describe this. I've stolen this from Jeff Patton and his wonderful book on story mapping. So iterative is the first line. So you're going to do the whole thing. You're going to create a sketch, and you're going to refine the sketch and improve it and fill in more detail over time. Incremental is the second line. This is the modular approach. We're going to divide the system up into bits, and we're going to fully realize those different bits and build up the picture over time. If we are going to build systems of any complexity, we need both of these approaches. We can't do it just one way. We're going to use a mix of these approaches as part of our engineering toolkit. We need to be experimental. An experiment is a procedure carried out to support, refute, or validate a hypothesis. Experiments provide insight into cause and effect by demonstrating what outcomes occur when a particular factor is manipulated. This is This is the kind of big one. This is the elephant in the room for me in many ways, because I'm a popular science nerd. I'm a fan of physics and that kind of stuff. And I would argue that human beings don't really do anything complicated without this. We don't just plan, I know, let's drive to Edinburgh. Well, Edinburgh's about over there. I'm going to plan over there. I'm going to drive over there. And if I drive at 70 miles an hour, it's going to take me this long. It doesn't work like that, because all sorts of things are going to change and get in our way. We're going to vary at a pace. There might be roadworks. All sorts of things are going to change our plan. That's the way that the real world works. And so we want to carry out a series of experiments, and we're going to kind of keep relearning and replanning. Jeff Bezos of Amazon takes experimentation so seriously that they measure the rate at which experiments fail. If more than 50% of the experiments that Amazon carry out don't fail, they increase the risk that they're taking. Because it's important that experiments should be able to fail. That's when you learn. You don't learn when the experiment fills in your understanding. You learn when it disagrees with you. And that's the wonderful trick of science. So I want to tell you another little story from the space program about this experimentation. And let's talk a little bit about the start of the Apollo program. In 1961, John F. Kennedy stood up in Congress and said, we're going to send men to the moon and we're going to bring them back. And all of the people in NASA, as they were listening to that on the radio or on the TV, went, because they had no clue how to do that. At this point in history, this was about 2 weeks after Alan Shepard had done was the first American in space. He did a suborbital lob. They strapped Alan Shepard essentially in a tin can on top of an intercontinental ballistic missile and fired him about 60 miles up, and he parachuted back down again. He was an enormously brave man. These things were blowing up on the pad all of the time, these Redstone rockets. He was an enormously brave man, but that's all they'd done. Nobody had been in orbit, no American had been in orbit yet at this point, and Kennedy's saying, we're going to the moon. We were having a chat about this before we started. This is kind of, if you've come across Dan Pink's stuff about, autonomy, mastery, and purpose, this is the iconic view of purpose. Kennedy's just planted a flag. He's just said, we're going to the moon before the end of the decade. I have no idea how to do that. You're smart, figure it out. Somebody said to me in a version of this talk, was this the biggest, most expensive user story ever? I think it might have been. It's definitely in with a shout. So Kennedy's just planted this flag. He's just said, here's the goal, here's the target. And all of the people at NASA have now got the problem of trying to figure out how to solve this problem. Here are some pictures of the things that they didn't know how to do. This is basically all of the things that you need to know how to do. So at this point in history, the Americans weren't having a great game, weren't in a great state in being able to launch rockets because they kept blowing up on the pad. When you see montages of this timing period, there were lots of explosions with the different rockets. You need multi-stage vehicles in order to be able to manage the energy budget. This is one of the key insights that happened very early on in the design of the program. But you need to do that, and they hadn't got that sorted yet. You need to be able to dock spacecraft together in space. Nobody done that, Americans nor the Russians. You need spacesuits. Nobody got that yet. You need spacewalks. Nobody done that yet. You need to do the recovery thing. Nobody had really done well. Alan Shepard was safely retrieved. Gus Grissom, who was the next person up on a Redstone rocket, his spaceship sank. So they hadn't got the recovery sorted either. All of this stuff they've got to figure out how to do. One of the answers, this is just kind of gratuitous to remind us that as part of the history, women made an absolutely crucial impact. This is Margaret Hamilton, the first person to coin the term software engineer. She was the first person to think of software development as a form of engineering discipline, and made a crucial contributions to being able to deliver the successful moon landing. In 69. But here's the problem. So here's the problem that the NASA engineers were faced with. Here's a picture of the Earth-Moon system. Except this isn't a picture of the Earth-Moon system. This is a kid's storybook. This is a picture of the Earth-Moon system to scale. At this point in history, no human artifact had been more than a single pixel away from the planet Earth. Nothing. Yuri Gagarin, Sputnik, the American suborbital lob, nothing had been more than a pixel away. So problem one, how do you get something from over there all the way over here? It's an incredibly difficult problem. So let's go and draw some Gantt charts, right? Not really. So there are too many things to go wrong here. So you can imagine the conversation the day after Kennedy's saying we're going to the moon, and you can imagine all the NASA the senior NASA folks sitting there going, how are we going to do this? We have no idea. I know, I've got a good idea. Let's build a spaceship, put 3 astronauts in it, send them to the moon and see if they come back. No, not a great idea. That's not a good idea, really, is it? I know, I've got a great idea. Why don't we build the spaceship, send it to the moon, but not put any people in it so we don't kill anybody, and then see whether it comes back? Well, it's better. We probably keep our funding for a bit longer and we won't kill any astronauts, so that's probably good. I've got a great idea. I've just thought of a brilliant idea. Why don't we send the rocket to the moon and land it on the moon, but don't bring it back? That makes it a lot simpler. That almost halves the problem. You're right, that's a great idea. Let's do that. That's really good. What does landing on the moon mean? It doesn't have to survive the landing on the moon to be useful. And that's where this came in. This is the Ranger program. And this was literally spaceships as bullets fired to see if you could hit the moon. That was the whole program. So the first mission, its job, remember I said about the spaceships blowing up on the pad? The first job was just to get one of these things into Earth orbit. That was the first mission. How did that go? It blew up on the pad. The second one, let's just do it again. We'll try and get it into Earth orbit. It blew up on the pad. If you've ever worked on a big project, the third one might amuse you. So the plan was, by now it would all be working. So the third one's supposed to go for the moon. So let's go for the moon anyway. We haven't been able to get anything to Earth orbit yet, but we'll go for the moon anyway. And they did get it into Earth orbit. They got it into Earth orbit because they'd learned from the first 2 failures. They did the deorbit burn, shot it off towards the moon, and missed. The fourth one, they got it into Earth orbit, they did the deorbit burn. Shortly after they did the deorbit burn, the spaceship died. All of the telemetry was lost, the cameras were lost, but they managed to track it from Earth-based stations, and they did see that it hit the moon, so progress. The fifth one, it missed again. The sixth one, it worked. It hit the moon, but the cameras failed. So they got telemetry, but no pictures. The seventh one was a success. The 8th one was a success. And the 9th one was a success. So you're NASA in the Cold War. You've got massive backing. You're on the front line of the Cold War with Russia. Imagine you get the phone call. We're trying to send men to the moon and we need your help. You've got access to all, the finest minds in the Western world. I'd go like a heartbeat. I'm sure you'd go if you got the call. You've got the access to the finest minds. How do you do this? Well, you start carrying out experiments. You start carrying out small little investigations. There were millions more experiments than this. Before all of this, there'd have been little experiments on the tensile strength of a bolt and all those kinds of things that added up to the learning. That's what engineering is. You carry out experiments. You don't build a massive plan for the next 9 years or the next 8 years to figure out how to do all of this. You'll have a rough guide to steer you in the direction, and then you experiment. That's how you do science, that's how you do engineering. I wanted to show a simpler version of experiment, just to try and make my point. Have people seen this kind of thing before? The idea here is to see which of the dots is bigger, the orange dot on the left or the orange dot on the right. Hands up if you think that the orange dot on the left is bigger. Hands up if you think the orange dot on the right is bigger. Hands up if you think that they're both the same. Okay, so nearly everybody's seen this before, so we can carry out an experiment, we can measure it, and they are in fact the same. It's an optical illusion. We can't tell the difference. Has anybody seen this one before as well? So there's two lines here, and the trick is to figure out which is line. Hands up if you think that the line on the left is longer. Hands up if you think that the line on the right is longer. Hands up if you think that they're both the same. See, you weren't paying attention. You've got to experiment. The line on the right is longer because I drew it longer. You can't tell. Guessing is not good enough. Measuring is the difference. Measuring is the difference between being a craftsman, which is okay, and being an engineer, which is better. We want to be empirical. We want to be empirical, based on, concerned with, or verifiable by observation or experience rather than theory and pure logic. I think there's kind of an interesting alignment. It seems to me that the sorts of minds that to which software appeals have something in common with the sorts of minds to which mathematics appeals. So we'll think of mathematics, as kind of, this fundamental starting point. And it's really important, but the first time you build a new Boeing jet, do you just put it in service because all the maths said it was fine? Or do you go for a little flight and you have a test flight program and you try it out? You do the second one because our models might be mistaken. There might be errors. So part of the way in which, actually, Boeing have quite a nice I've forgotten the word. They have a nice protocol that they undertake, which is the principal engineers that were involved in building the aeroplane are some of the first people that go for a flight on the aeroplane, which is kind of nice for a variety of reasons, not least that if they've got some skin in the game on making sure it's right. But maths is not enough. Maths is wonderful. Maths is a brilliant tool, but it's not enough on its own. We also have to verify with observation. We have to test it against the real world. Being evidence-based, being empirical, means that we can start to pull apart myths from truths. We can understand the things the points at which we're fooling ourselves and the points at which we're onto something real. We can start really making decisions based on data. And that starts us down this road to much more effective, higher performance outcomes. This only occurred to me fairly recently, but I think it's an interesting idea. We can never, ever be certain of success. However good our maths is, however good our formal proofs of our software is, or whatever else, we can never be certain because often that sort of thinking is harder than the kind of thinking that we do for designing our software and so on. And so there might be bugs in that kind of thinking. Our model might be wrong. There are all sorts of things that can go wrong. So we've got to find a way of being able to evaluate this in the real world and understand what's really working and what's not. Progress only comes when we risk failure. If we propose a hypothesis and define an experiment to test that hypothesis, and the experiment validates that hypothesis, that's much less valuable, actually, than if the experiment refutes the hypothesis. Because the experiment might be wrong. We might be fooling ourselves. We might be inadvertently biasing the results that we're seeing. If something surprises us, that starts us thinking. That's the point at which we learn, the point at which we start making great new discoveries. The transit of Venus across the surface of the sun at the start of the 20th century is one of the things that led people to start thinking, maybe Newton's wrong. And it started Einstein thinking about bendy sheets of space-time and general relativity. That's how science works. That's how real discovery works. It's being surprised and learning things. We learn most when reality doesn't match our predictions, and so we should be happy with that. We should be comfortable with being able to work in that way. Production will always surprise us. However good we are, it's always going to surprise us. And it should. If it's not, you're not taking enough risks and you're not learning enough. It's too predictable. This is the kind of realization that I had kind of recently. So all of our design choices, all of our coding, all of the efforts of our tests, all of the ideas in our heads, the diagrams that we have on whiteboards, everything, all of that, the software itself, all of that stuff added together, our understanding of the requirements from the user's point of view, all of that stuff together is really only ever our best theory at the moment. And we should be looking to try and work in ways that allow us to continually question our best theory at the moment and improve it. Is our build as fast as it can be? Is our deployment effective? Is it reliable? Is the user delivering on the value that our customers want? Is it nice to use? Is it effective? Could we develop these things more efficiently? Could our architecture be leaner and cleaner and more malleable? All of these things we can be looking to refine all of the time. If you think about it, it's kind of the way that science works. I confessed earlier on to being, my wife says that I'm a serial nerd. She's wrong, I'm a parallel nerd because I can be a nerd on multiple fronts at the same time. One of my nerdisms, as well as the Apollo stuff, is popular physics. So in physics, there are these amazing theories about the stuff on the grandest scale. The general relativity tells us about the Big Bang and how black holes work and all of that stuff. And it's phenomenally beautiful. The predictions of general relativity are accurate to within fractions of a millimeter out to the orbit of Jupiter. We have measured that. It's a staggeringly accurate theory, and it's wrong. We know it's wrong, and there are teams all around the world that are funded trying to come up with a better theory. That's how discovery works. That's how science works. That's how engineering works. We should be refining and improving all of the time. So our best theory is to explain things so far. All of that stuff is always that, and we should be always looking to improve and get better. So, continuous delivery as an engineering discipline. So the reason that I ended up talking about software engineering was really that I started thinking about continuous delivery in those contexts. I believe that when you really apply the techniques of continuous delivery full on, it gives you this massive step change in capability and efficiency. And it does that because it's the application of the scientific method to problems in software development. And the scientific method is humanity's best problem-solving technique, so it's bound to be better than not. We have short feedback cycles of test-driven development, automation, hypothesis-driven approaches, tests as a falsification mechanism. All of these things are things we learn from software. We've got the iterative approach to development, the feedback, the experimentation, empirical discovery, incrementalism. We've got these feedback loops around development. But fundamentally, this is it. This is the thing that we should be aiming for. And I'm sure that everybody in the room recognizes this. This is science. This is a description of the scientific method. We're going to make an observation of the world, of our users' desires for features. Whatever it is, we're going to make an observation. We're going to come up with a theory. And we're going to design make a prediction based on that theory. And we're going to carry out an experiment to test that prediction. And that can be at the level of requirements. It can be at the level of the quality of our code, the performance of our code, the deployability of our code, all of it, everything. One of the massive advantages that we have as a community over every other discipline is that we've got access to the almost perfect experimental platform. We can create little virtual universes inside our computers to evaluate our ideas. When we work that way, we see better results. So, in summary, I mentioned earlier that people have talked about software engineering as an analogy for what it is that we do. I'm not proposing that. I'm not saying let's be like software engineers. I'm saying let's be engineers. Let's start applying the scientific thinking, scientific rationalism to the way in which we work. Let's carry everything that we do, let's do that as an experiment. Let's learn, let's capture data, let's make decisions based on that quantitative data. Thank you very much.
Thank you, Dave. Any questions on that? I'm sure everyone wants to get some pizza, actually. There must be questions, right?
I've either stunned you into silence or you're very keen on getting to the beer. Either of which is fine.
Seriously, no questions. I've got one.
Sure.
how absolute do you have to be in this thinking? Can you do it part-time, or do you need to do it all the time?
I think that when you start working this way, it very rapidly infects everything that you do. I can give you a simple example. I'm a test-driven development practitioner. That's the way in which I write code, because it makes me design better code when I do it that way. So when I write my code, I'm going to write a test first, and I'm going to run the test, and I'm going to see it fail. What I do in practice when I'm doing that is that I'll write the tests to fail, and then I'll usually state out loud the error message that I expect it to report before I run the test and see it fail. Because that's my hypothesis, that I'm experimenting with the test. So I've taken this seriously enough that even that single test is a little experiment that I'm going to carry out to validate whether I'm thinking in the right way. And if it fails with a different error message, I've got my experiment wrong, and my implementation of my test is wrong. So I think it's very pervasive. I think you can start adopting it slowly, but one of the things that we were talking about earlier is retrospectives. The retrospectives are important because they close the feedback loop and give you the opportunity to start carrying out experiments. So I think it affects everything in which the way that you work over time.
Okay, we've broken the dam.
Lou, as a bit of a throwback to the last talk, how would you say continuous delivery applies as an organisation grows and at an organisational level, not just an engineering sort of way? So
I think there are a number. So as I said, one of the reasons why I use the NASA example, I mean, they were carrying out experiments on a massive scale, and it's divided up into a series of small teams. They've got different objectives, so it scales very well. As it is, science scales. I mean, it works pretty well. I think that it scales better than a planned approach, because you get beyond a certain size and you can't plan. It's too big, and so part of the game is to be able to break things into smaller chunks. There are a variety of different strategies that you can apply for continuous delivery. So Google take an approach, one approach, having big monolithic repositories and testing stuff. They're probably not the whole way in terms of the sort of discipline that I would think of in terms of doing continuous delivery. Amazon take a different approach with their small pizza teams and microservices architectures, where each deployment pipeline is fast and efficient. So there are a variety of different techniques you can use to scale it up. I think it scales really well, though. My fundamental point, though, tonight is less about continuous delivery and more about the engineering discipline, because I honestly believe that if you look at the history of success of any software project, it's fundamentally based on these sorts of ideas. It's certainly what was going on at NASA. The Curiosity rover was built using massive levels of simulation to evaluate the software and to evaluate what was going on with the whole system in test. These are the hallmarks. The Apple Mac was, there were design elements in the Mac that were specifically designed in. One of the first uses of ASICs in order to be able to program the hardware, so you could iterate quickly and learn quickly and recover from mistakes quickly. And I think that's a hallmark of solving any seriously hard technical problems. As I said, I think this is grounded in humanity's best problem-solving technique. So I think it scales very well, and I honestly believe it's the only way in which we do anything really complicated.
Hi.
Hi.
One of the questions around is, one of the myths is that people say that every engineer is a good engineer, especially software developer. But that's not my opinion. The question is, to do even that experimentation, it requires quite a craftsmanship.
Yeah.
To have that thing. Do you think anyone can become that, or does it have to be some sort of people? Because software development it needed a lot of developers, and it's very hard to get the right ones.
Yes, I think that's true, and I think that the explosive growth of software development as an industry is one of the difficulties we've been able to do. Start establishing this as a profession. It's not really a profession at the moment; it's a trade, because you can't get fired if you make a mistake, really. So if we wanted to establish it as a profession, then yeah, I think there would need to be some rules. I think that's part of the definition of what a profession is. And it might mean that this splits out into different camps. There might be, you know, a camp of people. This has been talked about for a long time, of some people that just assemble pieces, that are pre-prepared pieces in some way, and some people that do more deeper stuff. Maybe that's the way that it goes. My belief is that the process and approach is more important than the individuals, though. I think that, you know, within a certain normal distribution of general intelligence, you can teach people to do this stuff well. My experience, though, has been that there's not a very big difference between taking a computer science graduate, for example, and training them as a really good software engineer, and anybody from any other technical discipline. Physicists are pretty good once you manage to disabuse them of the impression that software is easy. because they're used to experimenting, they're used to scientific method. They'll take. I worked with a guy who had a PhD in chemical engineering, and he was absolutely brilliant in a disaster scenario because he'd be taking notes. It's that simple. It's, you know, he got the right training to observe an experiment. And when we do these smarter things, we all benefit from it. The other thing that I think that your question touched on is the idea of software development as a creative discipline. I think we often don't think of it in those terms, but it is. It's an intensively creative discipline, and I don't think engineering detracts from that. If you're Anita Sengupta who works on the Curiosity rover at NASA, you're an intensively smart and creative person, as well as a professional engineer. Engineer is not a, you know, I got a tweet about software is nothing like engineering because engineering is predictable, you get the same outcome every time. Of course you don't. That may be true if you've got effective production engineering, but that's not true of design engineering. Design engineering is about discovery, it's about learning, it's about creativity. And that's what any software engineering discipline would have to be, because that's our problem. Thank you.
Thoughts on driving predictability while using continuous delivery for a sort of product of moderate complexity?
I'm afraid that I'm not a great proponent of striving for predictability. In part, that's because of the kinds of software developments that I've worked in through the latter part of my career. I've worked in places where we were doing fairly innovative things, and innovation isn't predictable. Innovation is different to that. So you can work to timelines. You can optimize. Agile's brilliant at being predictable. You can optimize for that. But if you want to be working to maximize innovation or discovery or even pace, if you want to go for the fastest delivery, predictability is not the thing that you want to aim for, in my opinion. So I think you can get there. I think over time it's kind of interesting, but I don't think for me, I'm sorry to disagree, but for me that's not one of the measures of quality. The measures of quality is for me is whether software fulfills a user need and you know, does that in a predictable, effective way. You know, it doesn't break. You know, those are the sorts of things that are measures of quality for me. And so predictability isn't one for me. So that's not something that I strive for, and that makes it difficult sometimes to have some kinds of conversations in some sorts of organisations. But that is what I think it's about. If you, the Apollo program was working to a very hard deadline. Kennedy stood up and said when they were going to hit it, but it wasn't predictable. There were schedule slippages all over the place, all the way through, right up to the last minute. They were having an absolute nightmare with the lunar lander because it was such a complicated thing. And nobody ever built a craft like that before. So you know, I think it's a difficult thing to sort out. But you know, there are trade-offs. You don't get predictability if you're doing new, innovative things. And on the whole, isn't that what we're about? Isn't that what most software development is about? If we were doing the same, if we were writing the same software that we did last time, why don't we just use the software that we had last time? You know, if we're writing it, it's because we're trying to create something new. It seems to me.
I think that's all we've got time for.
Thank you.
Thank you very much.
Thank you very much.
Dave.
Thank you.
Thank you. Yeah, so that's it. All the speakers and the guy in the middle of them will be downstairs. If you want to ask any questions, I don't know if I mentioned it earlier, but we've been Coach Trip and we are hiring. If you want to find out how we do all that great stuff that Nick was talking about, I'm probably the guy to talk to, or Jeff, or Nick himself, of course.